In this lecture, we're going to calculate the pH and composition for an amino acid solution, which is a typical example of any diprotic species you might investigate. We're using leucine in this example, and the Zwitterion is highlighted here in blue. We'll give this amino acid a generic designation of HL because it has one ionizable proton in the structure. If we increase the pH, we see that we move from the center structure to the structure on the right, losing a proton in the process, as indicated by our pKa2 here, leaving us with L-. If we decrease the pH, this is a pKb process as we accept a proton. If we continue dropping the pH, leucine will pick up a second proton, giving us H2L+. Prior to this lecture, we reviewed how to write successive hydrolysis reactions, where acids donate protons to water, indicated by Ka1 and Ka2. We also learned that we can write the reverse of this process to reform the weak acid when a weakly basic anion accepts multiple protons, also in successive reactions, as shown by our Kb1 and Kb2 equations here. Keep in mind that the subscript 1 is given to the strongest acidic and the strongest basic form of whatever we're working with. Putting this information all together allows us to determine the pH and the composition of a diprotic system given the starting concentration of the predominant species. In this lecture, we'll start with a 0.0500 molar solution of H2L+, and solve for the equilibrium pH and concentrations of H2L+, HL, and L-. Our first step is to fill in an ice table with our starting concentration of H2L+. We see that we're going to lose X, gain X, and gain X to achieve equilibrium. And since this is our strongest acidic form of leucine, we'll use Ka1 to solve for the equilibrium concentrations. Transferring our expressions from the ice table to Ka1, we see that the X being subtracted from the initial concentration cannot be assumed to be small. So we have to solve this expression using the quadratic equation. Since X equals the hydronium ion concentration, we can also go ahead and solve for the pH. Next, we plug the value of X into the ice table to add a true equilibrium line of data. IC tables are actually the goal with diprotic systems because we have to transfer the information from this last equilibrium line to a new table. If you think about it, we know the pH, we have the concentration of H2L+, we have the concentration of HL. At this point, we still don't know the concentration of L-. So let's tackle that calculation next using the concentrations of HL and H3O+ and moving them to a new slide. The equilibrium data from our first acid dissociation becomes the initial line in our new ice table. Plugging the data in for Ka2, we get this expression where we have two concentrations that are essentially 1 × 10 to the negative second molar and an equilibrium constant that is much, much smaller than that initial concentration. This is great news because it means that we can cancel out both of the X's that are being added and subtracted from 0.0132 molar, and this literally leaves us with the answer since the concentrations will also cancel out. Filling in the last line, we can present an organized data table listing each of the concentrations when we take a 0.0500 molar H2L+ solution and allow it to reach equilibrium.